welcome to the numerical ship and offshore hydrodynamic course. Today is the lecture 9 and today we are going to discuss on the basic hydrodynamics. Okay. And these are the keyword that you are going to get this in YouTube. Now, we are mainly discuss the potential theory. Now, what is potential theory, that definitely we are going to discuss now. Now, in case of a water that we can take the following assumptions. So, the first assumption is that it is incompressible. Second one is this, it is inviscid. Third one is it is homogeneous, and then fourth one is it is irrotational. Now, what is the meaning of the incompressibility or inviscid, or when you say it is homogeneous or it is irrotational? Let us try to understand. Now, when I said it is incompressible, it means that the density is not the function of time. Now, it is not the case for gases, right, because in case of a gas it is adiabatic and it is compressible, it is the density is not constant over the time also. But in case of a water, we assume that it is incompressible. So, rho does not change with respect to time. Okay. Now, when you call it is inviscid, it means that I ignore the viscosity, and it is quite natural like to ignore the viscosity for water, because it understand it is very low, right. And most of the thing, like, because this course mainly focuses on the normal forces like radiation, diffraction, fluid Kirchhoff. So, that is why we really do not deal with tangential forces, okay, like drag forces, because wave resistance part is not considered over here. It is not the case always that we are not consider the viscosity. Of course, we consider in case of sea keeping also, when you calculate the roll motion. So, that time we do consider viscosity, and sometimes like when you consider very small tubular type structure, and we do for the long wave approximation, and we can use some Morrison equation. That time also we are consider this viscosity. However, in our ship waves interaction, and we are, if we try to understand that we are objective is to get the normal forces, which is radiation force, diffraction force, etc. At that time we can consider that viscosity is negligible. Okay. Next, we call is homogeneous. Now, when you call it is homogeneous, it means that rho is not the function of space also. Now, what is the meaning that rho is not a function of the space? Now, let us take a cup of tea and you add some sugar to it, and you do not stir it not firmly, like you just do it, and then you try to take the So, then what you get is that the first time when you take a sip, you cannot find it is not much sweet, right. So, as you take more and more, you can find the sweetness is more and more. It means that it is not homogeneous, that sweetness is not homogeneous, it is a function of space also. In the top level the sweetness is low, in down level sweetness is high. So, it is not homogeneous. Now, if you stir it firmly and for quite some time, then you can find that throughout the tea, in all time we are getting the same level of sweetness. So, then we call this a homogeneous. Now, in context of our situation, we are talking about the ocean. Now, in ocean, what is happening that you can say that salinity is not constant, right. So, of course, I agree salinity is not constant and it is varying over the depth. However, mostly we are dealing with some in case of the deep water approximation also, it will be hardly 80 to 100 meter. That is what actually we are going to take for this all this numerical evaluation and all, and we consider that is a deep water case. even if you take 150 meter depth, still the rho is does not change much, the side does not change much in this region. So, therefore, we consider here the rho is not the function of space also, and that is why I call it is homogeneous. So, this is at the property of the fluid, right. Now, again let me read out the first property, it is incompressible. So, we are not considering the rho is changing with the time. Second one is the I consider this inviscidness, that means that that water is not, I mean we are ignoring the viscosity term of course in the Navier-Stokes equation. And thirdly, we assume it is a homogeneous. So, rho is not a function of space also. Now, this is about the fluid, but what about the flow? We consider that flow is irrotational, right. Now, what is the meaning of when you say that flow is irrotational? Now, let us try to understand from the geometric point of view. Now, here you can see let us say these are the fluid particle, it is the path is in a red dotted line, it is moving in this path. Now, how it moves? Now, let us what we do is let us put a flag and try to see the flag when it actually moves, right. So, firstly I said when you call it irrotational, it does not mean that the fluid particle moving in a straight line, not necessary. So, that is why I take this circular path. Now, if I look at the fluid particle, now if it is coming from this to this point, you can see that flag does not change. So, it does not have any rotational velocity about his own axis, right. Now, in case of a rotational flow, if I try to do the same, then what we get is as follows. Now, you can see that as long this particle is moving from here to here and then from here to here, it has a rotational velocity, right. So, therefore, you can see that as it moves along this path, it also rotate about its own axis. So, in that case we can call this a rotational flow. However, mathematically speaking, if we consider it is a irrotational flow, so then what we do is we can say that curl of V, which is V is the velocity, equal to 0 or del cross V equal to 0. Now, this is a very important the mathematical concept that we are going to use, and for the potential flow theory, of course, we consider this is a irrotational flow and we use this property and also use a property like this is the typical is from the vector calculus, you know that curl of gradient of some scalar is always 0, right. That means, del cross grad equal to 0. Okay. Now, look at this. Now, if it is a irrotational flow, then curl V equal to 0, right. And also I know that in case of a is from vector calculus, you know that curl of grad of something equal to 0. That means, del cross gradient of something should be equal to 0. Now, suppose take a scalar potential phi, if I do this, then if I assume that V equal to some gradient of phi. Okay. So, therefore, since curl V equal to 0, so we can assume that V should be some gradient of phi, whether phi is some kind of scalar function, right. It is very natural, it is coming. Now, if I assume this, then this equation no one is automatically satisfied, right. So, in this case we call this phi is basically a scalar potential, right. And then the velocity, I can define this velocity of the gradient of this scalar function. Now, 3 component of velocity is u, v, w, that everybody knows it, right. Now, if it is so, then what is u? So, u basically the ith component del phi del x, v equal to the jth component del phi del y, and w be the kth component del phi del z. Okay. So, this is the you can see that these 3 basically my 3 component along the x, y and z direction, right. So, that is how we can define the velocity, and this phi is now is known as velocity potential, okay. And this is basically the backbone of the potential theory. So, when you call about the potential theory, you are talking about a function, a scalar function phi, such that V can be represented as gradient of this scalar function, and therefore, u equal to del phi del x, V equal to del phi del y, and W equal to del phi del z. Having said that, now let us try how I can rewrite my conservation of mass equation. Now, you know this is the general equation del rho del t plus del del x rho u plus del del y rho v plus del del rho w equal to 0. This is the standard equation, continuity equation. Now, in this course we are really not going to discuss how this equation comes, we start from this equation. Okay. So, here I assume that it is the rho is not function of time, it is incompressible. So, therefore, I strike out this term, right. So, if I assume that it is incompressible fluid, so then it turns out to be this equation. So, I just ignore the first term. Now, I use this homogeneity, that rho is not the function of space also. So, in that case, you know that rho will come out, and see rho is not equal to 0. So, I can strike out the rho also, and then we can find out that our equation is del u del x plus del v del y plus del w del z, right. Till this point, this is the equation for continuity if we do not consider that u is irrotational. That means, now I need to use the concept of the irrotational flow. Now, if you consider the irrotational flow, so therefore, we can write this u equal to del phi del x, v equal to del phi del y, and w equal to del phi del z, right. Pretty easy. Now, actually we are just almost at the striking point, where actually we need to substitute del phi del x here, del phi del y here, and del phi del z here. Once you do that, then we will get what? Yeah, we get the Laplace equation, right. So, this is the continuity equation for our potential theory. Now, it is very well known equation, right. And so, in our case, our continuity equation basically the Laplace equation. Now, you know that I mean somebody is from maths, they know very well about the Laplace equation, and also here who is dealing with the potential theory, for them also this is a very well known function, right. So, here we get my governing equation, or you can say that equation of mass or continuity equation is basically my Laplace equation. Now, you have once you have the Laplace equation, then so many things you can do actually, so many things the numerical solution you can think of also, right. We will discuss that, like once we know that this governing equation is a Laplace equation, so then how to solve this problem, okay, analytically or numerically. So, let us see. Before we go into this, let us try to get what would be the equation of motion. Now, this is a Navier-Stokes equation, right. So, here again we are not going to discuss how it comes, okay. And so now let us try to impose one by one the conditions. Now, first if I impose is a inviscid, so then definitely we are going to strike out this, right. And now if you consider this external force is basically under the gravity. Now, this is the force minus rho g. Now, if you divided this by rho, so it simply becomes minus g, of course, right. And if you assume this flow is irrotational, so definitely you can you can see that u equal to del phi del x, v equal to del phi del z and w equal to del phi del z. Now, if you need to do little bit of mathematics to impose everything into this equation, okay, and then you need to get the final term is nothing but the p equal to minus rho del phi del t plus g z. Now, how to do this? So, let's do this here. Now, here what we have done that. So, we are here it is so let me write in bigger way, it is del u del t plus u dot grad into u, right, and this equals to minus 1 by rho grad p and minus, as I said, you can simply write grad of g z. Okay. So, now, we need to substitute that u equal to del phi del x. I mean, these are the component. Remember, this is the vector u and this is the component, both are not same. Say v equal to del phi del y and w equal to del phi del z, right, that you need to do. Before that, try to find out what is this thing. Now, remember, since this u I know it is, as you know that I assume it is a irrotational flow. So, definitely you have to understand that del cross u equal to 0. Now, if you use this and then we are going to use one result from our vector calculus, which is that gradient of a dot b. Now, assume that del cross a equal to 0 and also del cross b equal to 0. If it is so, then it is a dot grad into b plus b dot grad into a. Now, in case of a and b, if you assume both are u, so then I can write u dot u is equal to u dot grad into u plus u dot grad into u, and then you can have 2 into u dot grad into u. So, we understand that u dot grad into u is nothing but half of grad of u square. Right. Okay, so let me write here half of grad of u square. Okay. So, now once I know this results, now I can apply u equal to del phi del x, v equal to del phi del y and w equal to del phi del z, and then the same thing I can get is it is del del t of grad phi plus or you can say the grad of half of grad phi square equal to minus grad of p by rho minus grad of g z. Now, you take everything this side and then you can write the grad of del phi del t plus half of grad phi square plus p by rho plus z z equal to 0. Now, since you can say this cannot be 0. So, this term equal to 0. So, you get finally that del phi del t plus half of grad phi square plus P by rho plus Z z equal to 0, and then finally, you can get P equal to minus rho of del phi del t plus half of grad phi square plus Z z. So, now if you ignore this quadratic term, so you can get this one, right. Okay. So, now, so if you now you can see from here that if you ignore this quadratic term, so this is your pressure equation. Now, here in this context, I would like to tell you that this is basically the major difference between the conventional fluid dynamics to this particular course, or maybe the when we do talk about the hydrodynamics or numerical ship hydrodynamics. Thing is that this is known also that Bernoulli equation, of course, you know. Thing is that in case of all other fluid flow that we are considering in mechanical, in all other discipline, aerospace, all other discipline, normally we keep the second order term and we ignore this transient term, which is del phi del t, right. You look at the Bernoulli equation, ask anybody, it says that P by rho plus half q square equal to plus sigma z equal to 0. So, we are ignoring the term, the linear term, which is time dependent term, and we are keeping that q square term. You see that in all Bernoulli equation we are keeping it, but here what we are doing is we are ignoring that quadratic term under the linearity. What is the linearity we are going to discuss later on, but here this is my pressure equation where we are keeping the transient term, which is del phi del t, and we are ignoring the second order, that grad phi square, right. So, here there is a big difference. Here we are really do not give much value to the quadratic term. However, the linear transient term is much more valuable. It is unlike the other disciplines. So, it is when you see what is the difference, what is the catch. So, this is the first time you can see there is a difference in the pressure equation itself, right. Okay. Now, let us move on. Now, this is the areas where actually these potential based methods are very successful. So, let us see. The first one is that we are going to discuss here, the computation of the motion in the floating body in COA, which is the sea keeping problem. This is very much successful. Remember that we say that is for the floating body, it is we are not considering the forward speed. Without the forward speed, we are considering the floating body problem, right. So, it is very successful. Second one is the computing the ship motion problem, that means the sea keeping analysis. Now, considering the ship motion or forward speed, it is not that successful compared to the floating body problem. Nowadays, everywhere any offshore industry, they are having some kind of solver based on the potential theory. Okay. But we do not see that popularity when you consider the forward speed motion, okay, as such. Of course, the strip theory is very popular, but not the 3-dimensional method as such. And of course, in propeller hydrodynamics also this potential theory is very important. Now, let us discuss some areas where this potential theory is not that appropriate or not that popular. So, one is the computation of the roll motion of a ship, of course, because it is viscous dominated, as I said that in beginning, that when you consider the roll. So, here the viscosity is very important. Okay. So, this is one area where actually we have to consider the viscosity, and then what we normally do is with respect to the potential theory, we add some viscous terms to deal with this. However, it is better to use direct the Navier-Stokes equation. Second one is the computation of the wave loads on a small structural member. As I said that Morrison equation here, normally we use this. So, here what it is under the long approximation theory, that means that the tubular structure is really small compared to the wave which is very high. So, in that case actually potential theory is not that popular. People try to because that viscous drag also very important in that particular situation. And of course, that ship resistance problem, it is directly related to the drag force. So, you cannot ignore the effect of viscosity. So, therefore, we can't, I mean normally we do not use popular the potential theory in this in such problems. Okay. So, today we are going to stop here, and from the next class we are going to discuss that how we apply this boundary value problem, I mean how to generate the boundary value problem using our basic governing equation is the Laplace equation, and what would be the boundary conditions, and then how I obtain the pressure using the Bernoulli equation. Okay. I mean that is from the comes from the Euler equation. Okay. Till then, thank you.